11. Conditional derivation. So far, we only have one method by which to cancel a show line direct derivation. In the present section, we examine a new derivation method, which will enable us to prove valid a larger class of sentential arguments. Consider the following argument. APQQR. PR. This argument is valid, as can easily be demonstrated using truth tables. Can we derive the conclusion from the premises? The following begins the derivation. 1 PQPR 2 QRPR 3 PR? 4. What formulas can we write down at line 4? There are numerous formulas that follow from the premises according to the inference rules. But, not a single one of them makes any progress toward showing the conclusion PR. In fact, upon close examination, we see that we have no means at our disposal to prove this argument. We are stuck. In other words, as it currently stands, derivation system SL is inadequate. The above argument is valid, by truth tables, but it cannot be proven in system SL. Accordingly, system SL must be strengthened so as to allow us to prove the above argument. Of course, we don't want to make the system so strong that we can derive invalid conclusions, so we have to be careful, as usual. How might we argue for such a conclusion? Consider a concrete instance of the argument form. If the gas tank gets a hole, then the car runs out of gas. If the car runs out of gas, then the car stops. Therefore, if the gas tank gets a hole, then the car stops. In order to argue for the conclusion of I, it seems natural to argue as follows. First, suppose the premises are true, in order to show the conclusion. The conclusion says that the car stops if the gas tank gets a hole, or in other words, the car stops supposing the gas tank gets a hole. So, suppose also that the antecedent, the gas tank gets a hole, is true. In conjunction with the first premise, we can infer the following by both exponents. O, the car runs out of gas. And from this, in conjunction with the second premise, we can infer the following by both exponents. O, the car stops. So supposing the antecedent, the gas tank gets a hole, we have deduced the consequent, the car stops. In other words, we have shown the conclusion if the gas tank gets a hole, then the car stops. The above line of reasoning is made formal in the following official derivation. Example 1 1 HRPR 2 RSPR 3 HSCD 4 HS5 SDD 6 R1 4 07 S2 6 0. This newfangled derivation requires explaining. First of all, there are two show lines. In particular, one derivation is nested inside another derivation. This is because the original problem showing HS is reduced to another problem, showing S assuming H. This procedure is in accordance with a new show rule, called conditional derivation, which may be intuitively formulated as follows. Conditional derivation intuitive formulation. In order to show a conditional AC, it is sufficient to show the consequent C, assuming the antecedent A. The official formulation of conditional derivation is considerably more complicated, being given by the following two system rules. System Rule 5. A show rule conditional derivation CD. If one has a show line of the form AC, and one has C as a later available line, and there are no subsequent uncancelled show lines, then one is entitled to box and cancel AC. The annotation is CD. System Rule 6. An assumption rule. If one has a show line of the form AC, then one is entitled to write down the antecedent A on the very next line, as an assumption. The annotation is as it is probably easier to understand conditional derivation by way of the associated picture. Conditional derivation CDAC CDASC. This is supposed to depict the nature of conditional derivation. One shows a conditional AC by assuming its antecedent A and showing its consequent C. In order to further our understanding of conditional derivation, we do a few examples. Example 2 1 PR PR 2 QS PR 3 P and QR and SCD 4 P and QS 5 R and SDD 6 pages 4, and 07 Q4, and 08 R1, 6, 09 S2, 7, 010 R and S8, 9, and I. Example 3 1 QR PR 2 RPS PR 3 P and QSCD 4 P and QS 5 SDD 6 pages 4, and 07 Q4, and 08 R1, 7, 09 PS2, 8, 010 S6, 9, 0. The above examples involve two show lines. Each one involves a direct derivation inside a conditional derivation. The following examples introduce a new twist: 3 show lines in the same derivation, with a conditional derivation inside a conditional derivation. Example 4 1 P and QR PR 2 P QR CD 3 PS 4 QR CD 5 QS 6 RDD 7 P and Q3, 5, and I 8 R1, 7. Example 5 1 P and QR PR 2 P Q PR CD 3 P QS 4 PR CD 5 PS 6 RDD 7 Q3, 5, 08 P and Q5, 7, and I9R1, 8. Needless to say, the depth of nesting is not restricted. Consider the following example. Example 6 1 P and Q R S P R 2 R P Q P S C D 3 R S 4 P Q P S C D 5 P Q S 6 P S C D 7 P S 8 S D D 9 Q 5, 7, 10 P and Q 7, 9, and I 11 R S 1, 10, 12 S 3, 11, irrespective of the complexity of the above problems, they are solved in the same systematic manner. At each point where we come across a C, we immediately write down 2 more lines we assume the antecedent, A, in order to attempt to show the consequent, C. That is all there is to it.